at the night sky. Every star, every galaxy, every flicker of light you see is part of a vast, dynamic universe. But here is something that might blow your mind. The universe isn't just big, it's getting bigger. Every second, galaxies are racing away from us, stretching the fabric of space itself. But how do we know this? What's causing it, and what does it mean for the future of everything? Stay with me, I will teach you how to calculate these distances from galaxies. To understand how the universe is expanding, imagine a balloon with dots drawn on it. Each dot represents a galaxy. When you blow up the balloon, the dots on the balloon move away from each other. It isn't just the dots that moving across the balloon, it's the balloon itself that is stretching. In the same way, aren't just flying through space. Space itself is expanding and carrying them along further out. This idea might sound strange, but it's backed by some of the most groundbreaking discoveries in science. And it's all started with a man named Edwin Hubble. In 1929, Edwin Hubble made a discovery that changed everything. Using the most powerful telescope of his time, he observed that distant galaxies were moving away from us. But here's the strange part: the farther away a galaxy was, the faster it seems to be receding. This relationship became known as Hubble's law. Hubble's law tells us that the universe is expanding uniformly in all the directions. It's like the balloon analogy. Every dot or galaxy is moving away from every other dot. But how did Hubble figure out this? The answer, of course, lies in something called an amazing name: Redshift. Light from distant galaxies travel across the universe to reach us. But as a expands, the light waves get stretched out, like a slinky being pulled apart. This stretching shifts the light toward the red end of the spectrum, a phenomenon called redshift. Think of an ambulance signal. As it moves away from you, the sound waves stretch out and the pitch drops. Light works the same way. When a galaxy moves away from us, its light waves stretch and the color shift toward the red. By measuring this red shift, astronomers can tell how fast a galaxy is moving away. Redshift is one of the most important tools in cosmology. It's how we know the universe is expanding and how fast it's going. Hubble didn't just notice that galaxies were moving away, he also found a pattern. The speed at which a galaxy recedes is proportional to its distance from us. This relationship is described by the Hubble constant, a number that tells us how fast the universe is expanding. For example, if a galaxy is 10 million light years away, it might be moving away at 500 kilometers per second. But if another galaxy is 20 million light year away, it moves at 1,000 kilometers per second. The fastest away, the faster it goes. The Hubble constant is like the universe speedometer. It helps us measure not just how fast the universe is expanding today, but also how it has expanded over millions of years. If the universe is expanding today, it must have been smaller in the past. Rewind the clock far enough and everything, all the galaxies, stars, even space itself, was compressed into an incredibly hot, dense point. This moment, about 13.8 billion years ago, is what we call the Big Bang. The Big Bang wasn't an explosion in space, it was the rapid expansion of space itself. Imagine the balloon again, but this time start with a completely deflated. As you blow it up, dots, galaxies move apart And that's what happened with the universe. It started small and has been expanded ever since. But here's where things get a little more stranger. In the late 1990s, astronomers discovered that the universe isn't just expanding, it's expanding faster and faster. This acceleration is caused by a mysterious force called dark energy, which makes up about 68% of the universe. Huge. We don't know what dark energy is, but we can see its effects. It's like an incredibly hand pushing galaxies apart. Some scientists think dark energy might be property of the space itself, while others believe it could be a new kind of energy field. Whatever it is, it's one of the biggest mysteries in our world. So, what does it mean for the future? If dark energy keeps pushing galaxies apart, the universe will become colder, darker, and more spread out. Over billions of years, galaxies will drift so far apart that their light will never reach us. Stars will burn out and new ones will stop forming. Eventually, the universe could become a very cold, dark, and empty place. A fate something sometimes called the Big Freeze. But don't worry, this won't happen for trillions of years. For now, we live in a vibrant and dynamic universe full of mysteries waiting to be uncovered, of course. The next time you look up at the night sky, remember every star, every galaxy, every bit of light is part of a cosmic dance, stretching and expanding in ways we are only beginning to understand. The universe isn't static, it's alive, growing, and full of mysterious waiting to be uncovered. Let's do some easy calculation to see how far galaxies are from us. Stay with me. Okay, here we are. And that's it. So let's calculate with simple formulas the distance of a galaxy with the wavelength we receive from them. So, as we discussed, the redshift and expanding universe. The redshift Z is a measure of how much the wavelength of light has stretched due to the expansion of the universe. It is defined as Z, the wavelength of the observed minus wavelength of the emitted light over the wavelength of emitted light from that galaxy. The wavelength of emitted is a wavelength of light when it is emitted by a distant object, a galaxy, star, whatever. And the wavelength of observed is the wavelength of the light when it is observed on Earth. So, of course, if the z is positive, is more than zero, the light is redshifted, meaning that the universe has expanded since the light was emitted. Hubble laws and the expansion of the universe. The Hubble laws describes the relationship between the essential velocity of a galaxy and its distance. So you can get the velocity, and by calculating very simple formula, you can get the distance of a galaxy. So the Hubble constant represents the rate of expansion of the universe. Its current base estimate as approximately 70 kilometer per second per megaparaseconds. So it's a huge distances. I will show you later. Then the essential velocity is related to the redshift by the following approximation for the small redshift. If it is very little than 1, then we can get this formula, the velocity by this. But if it is more than 1, we should use another method, which I will show you. And as you know, the speed of light is this. And for a larger redshift, as I told you, the relationship between V and Z becomes more complex and requires general relativity. And here we have the expanding universe. The redshift Z is related to the scale factor of the universe. The scale factor describes how the size of the universe changes over time. And if the scale factor is the Yeah, you see there 1 plus z uh, equals to the scale factor of the observed time over the scale factor of the emitted time. So what it shows us? It shows that if the universe is expanding, the z should be positive. That is the concept. So now we can calculate with very simple formula as I showed you. So consider that we have a galaxy which emits light with the 500 nanometer wavelength. We observe this light on Earth and measure it with the wavelength of 1500. By putting in this formula, we get the z number as 2. So one can ask, but how you can understand the wavelength of the emitted when you just receive another thing on Earth? That's a good question, but the answer relies on the spectral lines and atomic physics. Actually, the atoms and molecules emit or absorb light at the specific wavelengths depending on their energy levels. These wavelengths are like fingerprints for each element. For example, the hydrogen emits light at 656, 486, and 434 nanometers. Other material can emit in the other lines as you see in this picture. When we observe a galaxy, we analyze its spectrum to identify these emissions or absorption lines. By comparing the observed wavelength to the known rest wavelengths that we know for particles, we can calculate this number. So we go back to our formulas and we got the redshift number as 2. And here we have the c we put in this formula for calculating the velocity of the galaxy, which essential velocity will be 240,000 kilometers per second. And now we can get the distance of the galaxy from our galaxy, which very simple formula. You put the velocity and the Hubble constant, you get 3,428.57 megaparaseconds. If you want to convert it to the kilometer, you will get with this huge number, which is like 1.05 to the 10 to the power of 23 kilometers. It's a lot. If you are fascinated, you can calculate yourself with these very simple formulas the redshift, essential velocity, and the distances for the Andromeda galaxy M31, which is very close to our galaxy, and the GMZ11, which is far from our galaxy, and write it in the comment. If you like this video, please subscribe, like, and write your thoughts.